spring break, we talk about the CFA, and we have some other techniques. Okay, so we introduce the time series analysis by using the factor models, and also we talked about higher order factor models. And today we are going to apply some factor models to some old data. Okay, so we have some old examples that we can use a new method to try to look at adjust the old question. So first, we can have a review of the general SEM because that's SEM1's content. Okay, so we're gonna have a short review, and then we talk about the mimic model. Is called multiple indicators and multiple causes model. It's very, very simple SEM model. And we have a lab, and we're going to use different software to do the comparison. In section 2, we're going to go back to this matrix again. Remember when we talk about I forgot to record the answer. Remember that when we talk about the validity, we have, a huge matrix. We have some blocks. Okay, we have different colors. So it's called the model tree, the model method matrix. And we use different correlation. Is that large enough or small enough to look at the divergence validity, and also we have the discriminant validity. Now we are going to use factor models, factor analysis to try to do the data analysis. Okay, so this is more scientific way to look at the correlations. So of course we have lab. So section 1, review first. SEM. So now let's go back to look at these concepts. SEM can jointly investigate the relationship. Okay, it's about the relationship among observed and latent variables. For path analysis, we just focus on observed variables such as mediation, moderation, regression, something like that. And we're going to involve latent variables. After we talk about the factor analysis, we have different factors. Those are circles. Okay, we combine the squares and the circles together, trying to look at the relationship among them. So yeah, so for path analysis, mainly, path analysis focus on the observed variables. So we talk about simple linear regression, multiple linear regression, multivariate linear regression. Okay, so mediation, correlation, and we have factor analysis, which involves latent variables. Now we're gonna combine these two parts together. Path analysis and the factor models together. We have the full SEM. Okay, so general models combining these two. For example, mimic model. Today we're gonna cover this part. And also today we're going to cover this part. And we're going to modify the previous mediation models with latent factors. We will have an example, Use the older mediation model, but we introduce some latent factors into our model. So for your course project, you can do that. Of course, this introduction by including the latent variables should be based on your own literature, based on your theory. You cannot just use any latent variables to do the data analysis. And then we have some latent false models. Okay, so this is a review again. In general, we have different mathematical equations to describe the SEM. Okay, so we have, suppose we assume the intercept, the mean part is 0. Okay, we don't care about the mean part. So we have the X measurement model. This is the measurement model. This is the Y measurement model. So now we are clear that these two models are actually factor models. In SEM1, I didn't talk these two equations a lot because at that time we didn't talk about the factor loadings. We don't have the factor models. But after we learned that topics, it's clearly known that this is the observed variables. This is the latent factors. We have latent factor loadings. Factor loadings connecting these two parts, observed and the latent part, and we have the residual. This is for independent variable part, X part. And for the dependent variable part, why usually for the dependent variable part? Okay, we have observed indicators, observed items. We have written the factors data here, and the factor loadings. Again, factor loading gonna connect these two parts. Okay, common factors and the unique factors. Okay, this is two factors, and this is one. So dependent variable, independent variable. And then combine them together for structure model. So we assume that this is the relationship between the latent variables. So we have latent dependent variable, which comes from here. Okay, latent dependent variables. These are influenced by some latent dependent variable itself and some latent independent variables. So the latent dependent is here. Part of this influenced by some of the eta and also some of these C part. All of these are latent part. Of course, the latent matrix, okay, here, just like the factor loadings lambda xy, lambda x, lambda y here. So we have the latent matrix beta and the gamma to connect this relationship. Okay, so all the relationships are included in the beta matrix and the gamma matrix. Okay, and of course we have the residual part. So it's kind of like a multiple regression, but we focus on the latent variables, okay? Because we're trying to look at the true values instead of the observed values. And we have another form, okay, that is one form of SEM equations. We have another form called Bandler-Weeks model. So we combine three equations together. I don't care. In this case, I don't care if it's observed or latent. We just use one letter, okay, to show it's a dependent variable. Okay, this is eta is dependent variable. It could be y, it could be eta. Okay, it could be observed, it could be latent. We just use one letter to show it's dependent variable. And see here is the independent variable, and it could be observed, it could be latent. Of course, we have a lot of matrix. Okay, beta matrix, gamma matrix to look at the determine the relationship among these two. So this is called a Bandler-Weeks model. So it's the same thing, but here we use the factor models to decompose observed variables into the factors and the unique factors, common factors and the unique factors. Okay, so now let's look at a new example called mimic. Mimic is short for multiple indicators. Okay, multiple indicators. So that means we have multiple reasons. We may have, okay, a lot of reasons to cause the outcome. And also, oh, I'm sorry, this is multiple reasons. Okay, multiple indicators, that means, okay, multiple indicators, I'm sorry. So multiple indicators, that means a latent variable will have some observed variables. Okay, so some items is measured, that latent variable is measured by some items, okay, leading multiple indicators. And also at the same time, it has multiple reasons, okay, multiple causes, multiple predictors, covariates, background variables. So you will see, for example, we have people's age, people's gender, and the family background, or some other causes. Yeah, something like that. These are multiple causes gonna cause some latent variable. That latent variable will be indicated or measured by some items.
So is this typically used for the demographic part of our surveys?
You can say that, but it's more widely. Okay, it could be very, very wide. So let me just write it. Okay, multiple causes. That means we have some causes. Cause means, okay, the direction of the arrow is just like this way. These are causes, and this is outcome. And this is a latent variable. Multiple indicators. So this latent factor or latent variable has some multiple indicators. Okay, these are, you can see that item 1, item 2, item 3, item 4.
So that
are trying to measure the same latent trait.
So that could be like behaviors while the causes are like perceptions or behaviors and gender and
Yeah,
stuff.
these are reasons. These are reasons. Okay, these are causes. Okay. Or predictors. Causes 1, causes 2, causes 3. You have so many reasons to have this result, but this result is not directly observed. This is observed by these items. We just got these variables, this variable. It is not directly observed. The F actually is making the factor. Okay, it's not there when we collect the data. This is newly created when we do the data analysis. Yeah, so this is a very, of course, we have a lot of like residual. Okay, so we have a lot of unique. We have a lot of residual. And we have some covariance or correlation among them. Okay, so we have some correlation, covariances among them. Okay. So for mimic model, we usually focus on single latent factors. Okay, so we just look at one F here. So this is a path diagram of the mimic model. Yeah, again, what we observed is just these a bunch of variables and these a bunch of variables. No, the center part. Okay, the center part is not there. We're trying to look at the latent factor. So we look at we use an old example. We use the data set we analyzed before. It's called active data. We have advanced cognitive training for independent and elderly. So we have different cognitive actually these are latent variables. Okay, memory ability, reasoning ability, speed ability, and we have a bunch of tests. Okay. So these are several of these tests. Okay, LS test, WS test, HLTT test, LT test, MPT test, all of these tests. But we do have some other background variables. For example, people's gender, participants' gender, participants' age, their educational level. Okay, so these could be our causes. So these reasons, these are reasons. All of these gonna influences not the students or the participants. These are elderly people. All of these will influence the outcome or the test score of these variables. Okay. So this is the old example. When we use a mediation, we have this is test diagram. So we have age, people's educational level, and we have the memory test. Okay, we use HBLTT to test the memory. And we have 3. These are actually, if you look at the tests, these are actually reasoning. So you didn't say anything about this. These are actually reasoning items for indicators. But anyway, so let's just look at the old example. So we have WS, LS, LT, all of these are tests. And we have the outcome. Okay, EPT. EPT is short for the everyday problems test. Okay, everyday problems test. So we're gonna look at the inference of EPT. Okay, so we have different memory tests and reasoning tests. Yeah, so by looking at these 3 tests, we know that all of these are indicators of reasonability. So our goal is trying to get the reasonability, but we use these 3 tests to obtain the scores, to measure it. Okay, so these can be treated as one measurement model, or we can use a factor model to summarize the scores here. Okay, this triangle part. So 3 tests or 3 items, 3 indicators. We have one reasoning ability. Okay, so we add a circle among these 3. Okay, add a circle into this model. And of course, we still use these 2 as our covariate. Okay. Then what is the path diagram now? So we want to use the path limit model. So now let's try to modify this general path diagram. So we only have two causes. So in this case, example, we have age and EDU. Okay, so we have participants' age, not always that person, and the EDU, educational level. We only have two causes. And then we have the F here. The F is called reasoning ability. Okay, reasoning ability. And we have three items. We have three tests. Okay, so we have this is the WS test. This is the LS test. This is the LT test. Okay, we have three tests. Previously, we just focused on this observable test. And now we're gonna introduce the memory ability between them. So this, of course, we have the covariance among them. We have the variance of age, variance of EDU. Okay. So that is our this part. Yeah, including this part is just our factor model. Okay. We have one factor here, we have some observed variables here, we have the here. So we just change the path diagram into a factor model. Right, so that's it. In order to translate this path diagram to our M+ code, so let's try to look at the beginning part. So we have title. Okay, this is called mimic model. You can choose the title name, the data, the mimic M+. Okay, the format by using M+ without. Okay, we use a data set without any title or the column names. So this is a data file and the variables. Okay, so in that data file, it's already simplified. We don't have the EPT. Okay, we try to make the mimic model simple. So we have EDU here, we have here it's not age, we use gender instead of age, okay? So we change the variable here, we use gender. Of course, you can use age, okay, but in our code, we use gender. It doesn't matter, you can use age, okay? But just follow the code, okay? We have gender, female or male, and we have WS, okay, LS, LT. That's it, okay. So those are 5 observed variables. So we're gonna use all of these 5 variables. 2 causes, 3 indicators. We're gonna use all of them. That's it. And then what is our model? Here, okay. R5. What does that mean? I created one variable. By using by, that means I created a new variable with latent called R, which is measured by WS, LS, LT. So this is the measurement model or the factor model. And also, in addition to that part, I also have R on. Remember on is regressed on. This is a regression. This part is regression. Okay, this part is regression. R dependent variable is regressed on gender and EDU. Okay, R regressed on. R is regressed on dependent variable, independent variable 1, independent variable 2. And we're gonna also look at the covariance among these 2 independent variables. Okay, gender and weight, EDU. That's it. This is our M+ code. So let's try to look at the output. So if you go to the ELC, okay, let me upload the data file. Okay. So this is the data file, and actually you can just type in the code, or I can give you the code here. The same thing. So you can just download the mimic one because by using the different application, you can have mimic two. Download this data file and the code and open M plus and open the file, mimic one. Okay. And of course, you have the data file ready. You're gonna save the data file in your local folder. Okay, so let me make it larger. Okay. So the name of the file, download it and save it to your local folder. And actually, you can look at the file. It's just five columns. Yeah. Oh, this is. Oh, it's mimic and plus. So I'm sorry, I download. It's not active here. So we have another example. So it's mimic active. So okay, mimic plus. Okay, just download the mimic and plus. The second example is here. We have 5 columns. Okay, first column, second column, third, fourth, fifth column, and the column names are shown here. Okay, PDU, gender, WS, LS, LT1. Okay. So gender have 2 values only, 1 and 2. So that means gender and a male and a female. Okay, so if you look at the code, okay, 1 means male, okay, 2 means female. Okay, so we have 2 outcomes for the gender. And yeah, so let's try to run. Let's try to run the code here. Okay. So yeah, let's just look at the code. Okay, R by these 3, R on these 2, and the code vary between these 2. Then we can just click the run here, the red button here. Run. Okay, so immediately we got the output like this. So again, let me make it larger.
Oh, I can read that.
Yeah, okay, that's the beginning part of the input file. Okay, just input the syntax, and this is a title, and the algorithm part or the data part. Number of groups 1, the number of observations 1,114. Number of dependent variables 3. Why? Number of dependent variables 3. These are indicators. Okay, so because R by these 3, these are 3 dependent variables. Okay, so number of dependent variables 3, and then number of independent variables 2. Which 2? Here, okay, are on these 2. So these 2 are independent variables. Okay, these are 3 independent variables. And then continuous latent variables 1. Okay, number of continuous latent variable 1. Which one? Which is R. We created it here by using by. So this is a latent variable. So that's a question.
So the way that this relates to CFA is that essentially we're just telling it R, when you create latent variable R, you're simply telling it to do a 1-factor CFA with those variables.
Exactly.
Right.
Yes, you're right. Yeah, exactly. Yeah, thank you. Yeah. So we created R by using the factor model. This is factor model. If you use by, that means we have factor before the by, and we have three indicators after by. Okay, these are three dependent variables. So three dependent variables. Actually, it also tells us, okay, observe the dependent variables here. Okay, these are these are dependent variables, WS1, LS1, LT1. And then these are independent variables, okay? EDU and gender, these are two. And the latent variables, this is R, this is the latent factor, okay? So all the information variables are summarized here. And then we have the algorithm information, okay, estimator, we use the maximum likelihood estimation method, the information we use observation and the number of iterations, okay, convergent criterion, so we have the algorithm part, input file, this is our input file, okay, data file, format, free format, we don't have any format, because it's text format, okay, free format. And then the univariate sample statistics, so descriptive statistics, variable names, sample size, okay, all of these are 5 variable names, number, okay, sample size 1114, mean variance, skewness, kurtosis, minimum percentage, okay, maximum percentage, and the 26th percentile, and 48 median. All of these are reported here. These are very general descriptive statistics. And then let's look at the model fit, okay? Number of 3 parameters. Likelihood, BIC, BIC, chi-square, value, implicit freedom, RMSEA, TFI, TLI. This is for the baseline model, okay, the notice part, okay. SRMR, so those are model fit indexes. And then we have the model results. These are estimates of parameters. All by these 3. Factor loadings, these are factor loadings. By default, the first factor loading has been fixed at 1. So this is the default way in M class. If we didn't do anything, so this is the way to identify your model. Of course, you can release this fixed value. You can use star to release this factor loading, and by fix the variance of R at 1. Okay, this is the other identification method. By default, they fix the first factor loading at 1. And then we have the lambda for LS, okay, lambda for LT. And this is the regression part. Regression R on EDU. This is the coefficient of the regression, okay? Coefficient of gender. This is the covariance. EDU with gender. This is a negative, okay? EDU and gender negatively correlated. And the mean part, intercept part, variance, okay, variance of the EDU, variance of gender. Independent variables, okay. The variance are reported here, the covariance are reported here, so the independent variables are done. And then residual part, residual for LS, residual for WS, I'm sorry, residual variance for WS, for LS, for LT, and also for the latent variable, the latent R, reasonability, it also estimated. But if you want to fix, okay, if you're trying to identify the model by fixing the variance of R at 1, then the first factor loading will be released, and all of these will not be existed because it's fixed. So 2 ways. This is by default the first way. So you can, that's our first method, and you can also look at the second method. So let me try to upload the.
Is the mimic only available in the N plus, or is it available in?
Yes, yeah, okay. We're gonna look at the code again. Yeah. So
okay, Lavana is what I was figuring.
Yeah. So mimic. Mimic 2, okay. So you can download the Mimic 2 and plus code. Actually, it's the same, almost the same. Okay. And then open that in M plus. Now let's look at the difference. Okay, so everything keeps the same except this part. Okay, except here. Except R by the first indicator here, we use star to release the fixed value at 1. Okay, so otherwise the first step the loading will be 1. Instead, we fix the variance of the R at 1. Okay, this means a variance of R and the fixed at 1. This is another way to identify your model. So the factor loading of LS1 will be estimated, but not the variance of R. Okay, so everything keeps the same of this part. So if you run this method, okay, so repeat everything here, and summary of data part, yeah, I just repeated here, and this is the same result. And yeah, model shade is the same. So that's a difference. Okay, here, not in the model results. The first factor loading here, now it's not 1 anymore. It's 3.87. Okay. And the variance of the R has been fixed at 1. So that's the only difference. You can do the comparison. Let's look at this one. This is outcome. This is outcome from the first identification. This outcome from the second identification. Yeah, so if you do the comparison, everything's the same here. Everything is the same. Model fate, yeah, just trying to look at the model fate. Yeah, the model fate. Exactly the same. Okay. Yeah, all the model fate indexes are exactly the same. And the estimate, okay, this is different because we changed the scale. So this part is different. This part is different. So in this first method, we fix the first loading number at 1, but here we didn't do that. So that's why these 3 numbers are different, but the ratio is the same. If you rescale of these 3 numbers to assume this is 1, then this number divided by 3.887, it will become this 1.178. The scale is the same. If you divide this number by 3.87, then this number will become 0.431. So it just rescale these numbers. And the same thing here. Okay, so if you rescale everything, then you will have this set. Covariance is the same. Okay, so covariance between these 2 independent variables. Okay.
Can you give an example of how that would be interpreted?
Yeah, last slides.
Oh,
yeah. So yeah, okay, yeah. Let's just think about this way. We can do it right now. So what does that mean? So in this case, the reasonability, because it's latent, we don't know what is the scale. We don't know the unit because it's latent. It's unobserved. Then we use one way to give a unit. So that means one unit increase in R is the same as the 1 unit in the WS change. So WS is word series some test. Okay, so if we have 1 point change here, then we will have 1 point change in the latent reasonability. By this way, we try to fix something to make this reasonability measurable. Otherwise, it's latent. We don't know what's the scale. We're gonna use centimeter. We're gonna use foot or inches to measure something. We don't know. But by using this way, we fix that as the same unit as the word series. And by using this way, we try to fix the variance of the R. Okay, so here, we try to fix the variation of R. So each variable has a mean, has a spread. If we fix the variance, the spread of the R, we also fix something of this latent variable. And then we can do other estimation. It's kind of like we put another scale on this latent variable. These two sets are exactly the same, but we just use different unit. Something, for example, we use a centimeter. Other sets we use as inches. So the results are exactly the same. If you check the model fit, it's the same. But the interpretation is a little bit different. Yeah, the identifying method is a little bit different. Yeah, we have some other the means of this part is for the mean part. Okay, so far we didn't talk about the means. We just focus on the variance and the covariance. Later on, we will combine the mean part back to the SEM one. So this is the mean of the EDU gender. This is the mean of the EDU gender. It's the same. Intercept, okay, it's the same. This part and the variances of EDU and the gender. These are the same because these are observed variables. These are not latent. So all the observed variables have the same output. Okay, EDU, we have the EDU outcome. And the gender, we have the gender variable. So all of these are fixed. We don't have any change. Just like a covariance between these two. Okay, these are fixed. These are not fixed. These are estimated by these two columns, by these two observed columns. So we don't need to do the identification. Okay, so we have the residual variance. It's the same. Okay, residual variance for WS, okay, for LS, for LT. But the only difference is the latent part. Is the latent part. We have to fix something to do the estimation. So that's that's a model. That's a code. Okay, so you asked about R. Now let's try to use R. So any question about M class? Done? Okay, now let's look at R code. Okay. Suppose we use a Lavon package. And this is the code. Okay, so we have the working directly. We have the we call the data. The name as the data is different. Okay, because for this data set we have the title. We have active title, and we have more columns in this bigger data set. And we pick some of these. Okay, we pick EDU, gender, WS1, LS1, LT1 to make a smaller data set called the new data. So this is a huge data set active. So include a lot of columns. We just use these 5 columns among them. And we call it a new data. Okay, new data is an active subset. Okay, subset of active by taking these 5 columns only. And then we try to use library, Lagrange. This is our model. Okay? It's quite similar as our M class. Okay, mimic model, we just call this model is named mimic. Or use equal tilde, okay, equal tilde, okay. This is for regression, okay, this is for regression, but this is for measurement model. This is for measurement model equal tilde. Or is created by this statement. This is a this is a new variable. Measured by is measured by these three variables. And also R is regressed on. So tilde here in the long package means regression. Okay, it's regressed on. So R at the same time is also regressed on these two independent variables. These are three dependent variables measured by three indicators or dependent variables. And R also is regressed on EDU and the gender. So that's it. This is actually the same as M plus code here, okay? R by these three. In Lagrange we use equal tilde. R on EDU gender. In Lagrange we use tilde. Okay? It's quite the same. Okay? But in R we have to use plus to connect these dependent variables or the variables.
But what about that third line, the EDU with gender?
By default, the Lagrange package will just give you that the correspondence. Yeah. So that is the model. This is our model. Model is ready. The data is ready. So we have two parts. Okay, data part, model part. Trying to mix them together. Okay, so we have model part, data part, and we use SEM function inside the Lagrange package to do that estimation. The result is saved here. So result is called mimic result. Of course, you can change the name of the result. And then we can use summary to look at the inside of the result and use a fit measures to look at the model fit indexes. Okay. Yeah, so this is a notation. This is the notes. It's notes for the tilde. Okay, I think let me have the R code. So you can open R Studio and download the R code. Okay. And you can change the working directory. So let me check. Yes. Okay, so let me upload the code to DLC. So it's called mimic class .r. Okay. And the file is active, I think. Active text. Data file, active text. So download the active.txt and mimic class.r and open R Studio, open R Studio. So that's a code. And well, we can use this one. Okay, so we can open file. Okay, so that's the code. And of course, okay, here I didn't give you the detailed path because you're gonna choose your own working directly. So you're gonna change this part, or you can just directly go to session, click session, click set working directly, and then choose directly and choose a file. So choose a folder where you save your data file and your code. So that is my path, okay? Then you're gonna change your own working directly. And then this is my data file, so active text. Here we have header for R, for the R code. I have all the columns available. So header should be true. I'm gonna include the first row as column names. So by using the read table, and I save it to active, you can check the data by using the head, okay? So here, the original data set is huge. So see, we have so many columns. So we have the first session, we have second session, we have third session, we have 6 weeks. Okay, so we have 6 sessions. This is the original data set, but we don't need to use all of them. And also we have training, we have group, we have a lot of variables. We only needed to use these 5 columns. So by using this way, use variable, okay, I choose these 5 columns and then get a subset from the whole active. So by highlight these 2, I click run. Oh, UV is not founded. UV. Oh, sorry. This is okay. This is UV. Okay, this is UV. Because I use different space, and then I just run again. So by checking head, by using head, you can check the subset, because this is much smaller subset, a much smaller data set. We only have 5 columns. So we're gonna use the new data to do the data analysis. So the run package, first, we need to check here. Okay, the right panel in RStudio, we have the bottom part. We have a tab called packages. And then check all the available packages in your computer. Okay, so here we have Lava. I see that there's a Lava. Then check the box in front of Lava. By using that way, actually, by using the library, it's the same thing. Okay, you can manually run library this package. But of course, you have to make sure the Lava package has already installed in your computer. Otherwise, you're gonna click the install here. Okay, this is another tab here, install, and then type the package name here and click install. So automatically they will just install the package in your computer. But here it's already here, so we don't need to do the installation. So we have already used the library, make it ready for us to do the data analysis. And the next part is to define the model. So define the model. Oh, here. This is weight, okay? So you asked about weight. This is a weight. We use 2 tilde. 2 tilde. Tilde is a weight. Okay. So EDU and the gender. We also would like to look at the weight, the covariance among them. Covariance among these 2. So R is measured by these 3. R is regressed on these 2, and EDU tilde covariate with gender. So we're gonna check the covariance among these 2. Actually, if you ignore this one, I think that let's check. Let's do the comparison. Okay. So anyway, we can highlight this part to define the model. This is our mimic model. Okay, click run, and then we have the SEM statement. So SEM, this is our model. We just defined here. This is a data set. We just extract from the larger fixed data set here. So make these 2 parts available. And here, this is option. Okay, if you're trying to fix the variance of the R, variance of the latent variable at 1, then you're gonna use this option. If you don't want to do that, you can just make it off or delete that. By default, it's F. So let's try different options. First, make it true. Then the variance of R will be 1, okay? And the summary and the fit measures. So we can highlight them together. And click run. So we have output listed here. So this is output. So after 26 iterations, so we have to do the iteration to get the final conversion result. And we have the estimated, we have the converged estimate. And the beginning part or also the algorithm part, number of observation, this is sample size, this freedom p-value, okay, model, chi-square value. Here, okay, this part, latent variables. Here, this is the factor loadings. Because we fix the variance of R at 1. So the first factor loading is really estimated. It's not fixed at 1, okay? It's really estimated. So we have factor loading for WS, factor loading for LS, factor loading for LT. So if you do the comparison, this result is the same as the R output. So if you have the R no, I'm sorry, the M plus, okay, the M plus output, it's here, okay, this is M plus output, yeah, M plus here, if you check R, here, yeah, it is the same, okay. Okay, so 3.77, I'm sorry, 3.887, 4.613, 1.674, okay, and the standard error is 0.11, okay, 0.1, okay, here we have some rounding errors. In R, we have 0.126, in M plus 0.125, it's totally fine because it's just rounding errors just like this, okay. So here we have 0.067, 0.066. It should be considered as exactly the same. And this is the regression part. Okay, this is the regression part. In M plus, we have 0.2, 0.014. Okay, and in R, we also have 0.2, 0.014. Standard errors, yeah. And the covariance, okay, covariance is good. We have the Lavan output, we have transplant output, and errors. Variance is it for the residual variance, okay? Residual variance. Yeah, residual variance here. Residual variance. And for WS, here, this is for WS. For LS, for LT. And the EDU and the gender are recorded above. Okay, so EDU here, 6.754. Okay. For gender, 0.177, and R is 671. R and M plus that's also the variance of R 671. And you can also compare the residual the standard errors. Standard errors in this case are not exactly the same. Let's check the results for WS. We have standard error like this, report like this. But in M plus, we report that this number, so they are different actions. They are different. Yeah. It's But for ED and gender, they're the same. But for these three, the standard area response, they use different algorithms. So that's why we have the different standard area estimate. Here, the parameter. Okay, so information matrix. They are in R we use expected information matrix, but in M plus I think they use observed information matrix. Information matrix they use observed information matrix. So the variance part is different. So here we use the expected information matrix. So the variance part of the standard area, okay, the estimate of these are different. Okay, so that's a Navan package part. Any question? Yeah. So just like we did here, so your final project, if you trying to create a data variable, if you want to use R, you can just follow this code, okay? And plus, if you want to use M plus, then you can follow that code. And you have to provide the code in your final project. Okay. First, you describe your data file and then describe your model by using the path diagram or equations, and then provide the code and then look at the result. Also, you're gonna provide the result, either R outcome or the M plus outcome. And then you also gonna do the explanation. Yeah, we will have the explanation in the last slide.
Can we meet with you one-on-one to kind of show you what our data looks like to
Yeah,
make
so
sure?
we have the Q&R session. Yeah, we can do that. Yeah.
Okay,
Yes,
because
yes.
I want to make sure I avoid what I did last year and use shitty data,
Sure, yeah.
so.
Okay. Okay, so that's level one. Any question? So we also learn SEM. SEM also is a very good package, although we have a long runs. Okay, we have a larger model specification, but actually in this case, we have all these parameters specified. Okay, we have lambda 1, lambda 2, lambda 3. So we have the coefficient for ED to R, we have coefficient for gender to RD, okay? We have variance fixed at 1. This is the variance of EDU. This is the variance of gender. This is a covariance between these two. Residual variance of WS, residual variance of LS, residual variance of RT. So this is very clear. For SEM, all the parameters are listed here. So that's why in the beginning I introduced SEM, because this is a very, very good package to do the introduction to the software. Okay, but it's quite long. So if you have more parameters, you're gonna increase the number of runs here. And in SEM, you also need to know the covariance matrix. Okay, so S should be calculated here in the beginning of this part. So you have new data, 5 variables. You're gonna create a covariance matrix of the new data. It's 5 by 5, 5 by 5 covariance matrix. It's called S. So S is information here. So you need to input the model. You also need to input the S and sample size. Sample size, you use the N rows to calculate the sample size. And finally, you have the result of the SEM. You can use summary to do the data analysis. So suppose we're gonna use SEM package. Let's go back to the R. Yeah, this is the one package. Now I'm gonna use SEM package. And we're gonna change the package. So in the right panel, uncheck Lavon. Okay, so Lavon. Uncheck, and then find the SEM, check SEM. Here, SEM. Okay. So here. Check SEM. Okay. So now actually what we did is detach the package of Llama and then use a library to attach a new package. And we just try to run the code in SEM. So that's it. So first, sample size. How are you going to get sample size and rows? Okay, n is how many? Okay, how many rows? Number of rows in the original data set. So n is 1,114. So it's saved n here. And then S, what is S? Is a covariance matrix. Covariance matrix of the new data. Okay, we have 5 variables. So 5 by 5 is S. So you can check the S here. Capital S, okay, case sensitive in R, capital S. That's it. This is a covariance matrix. This is the covariance matrix. Okay, 5 by 5. Covariance matrix. EDU, the WS1, WS1, and T1. Okay. Then this is our model. Okay, this is our model. Mimic model. Mimic model. I'm gonna highlight everything inside the function of specified model. So everything should be highlighted and rounded together. 3 factor loadings. R goes to these 3. Okay. And also regression part. PD and gender goes to R. The variance part. The variance of R, the variance of PD and gender, covariance. So everything's here. And then we have the mimic SEM result. Okay. The highlight is one. The result is the key. Okay, so that's the result. Model Pascal, okay, degrees freedom, and ANCDLC, normalize the residual without residual bar, squares for the different variables. Then the estimate. Okay. Then the estimate. This is number 1, number 2, number 3. These are explained here. Okay. Number 1 is R goes to WS1. Number 2 is R goes to LS. Number 3 is R goes to LT. So all of these are estimated here. And then if you check the numbers, it should be the same. So if you, again, we compare it with M plus here. Okay. So 3.88. Oh, it's different actually. You can see that it's not rounding error this time. It's okay, 3.88. No, it's 3.87. So by using different packages in R, it's different. Okay. And here it's 4. It's also different. Okay, so in SEM package 4.615. It's 4.613. Okay. And some areas a little bit different. If you round it up, it should be 1.126. It should be, if you round it up, it should be 2112. Okay. Number 3. It's also different. 1.675. Okay, here 1.674. And if you round it up, it's also different. G, what is G? G is regression coefficient from EDU to R. This is the same. Rounded up is the same. This is also the same. Seven errors is the same. This is the same. And these three lambda factor loadings are a little bit different. Check the variance and the covariances. Covariance. Okay, it's the same. Because these are observed variables. ED and gender are observed variables. So you have to according to 257, but this is also the same. As long as 2. What is as long as 2? As long as 2 variance and the EDU and the gender. Yeah. This should be exactly the same. Okay, 6.0. Even this is different. 6.76. It's 6.754. S1 also a little bit different. Okay. If you round it up, it's 0.178. Residual. It's different. LS. It's different. As 0.7. This is LT. Different. So you can see that if we use different package, the results are not the same. It's not due to rounding errors. It's quite big. The difference is quite big. So you should specify what kind of like a model or what kind of software, what kind of package you used for data analysis. Okay. And these are model fit indexes. Indexes are basically here. What do you self-fit? Let's check the CF5 here. Let's see. Very similar. Okay, that's one way to identify your model. If you're trying to use another way to identify it, then you're gonna change your option here. Okay, suppose you use, if you're trying to use the other model identification, then you add one row here. So if you use this way, without this option of standardized fixing variables, okay, it's true, then you will have the first affect the loading fixed at 1. So you can also run this code. Oh, now you're gonna use Laverne. So you're gonna use Laverne. This is your model. This is your model again. So you have this one. Summary. In this case, the model identification is different. So the first affected loading has been fixed wrong. It's just like the first method of in SEM. Actually, if you check the details of M plus outcome, this is a warning message. The standard errors of the model parameters estimates may not be trustworthy for some parameters due to a non-positive definite first order derivative product matrix. This may be due to the starting values. Okay? So this may be due to some, but may also be an indication of model non-identification. So the condition number is small. Okay, problem solving the following. So let's check the outcome. So see which variance is negative. So estimate. Nothing is negative here. So the variance of these three are positive. Residual variance, all of these are positive. Okay. So which part? It seems okay. I said the so that's why we needed to do the modification. Next class, next week, we're gonna fix all of these problems. So by looking at the modification model problem involving the following parameters. Parameter 16, gender. Parameter 16, gender. Gender, the variance is here. It's the same. It's okay. Psi. Okay. Psi, gender. Okay, let me just tell you how to debug or how to read those warning messages. So in M class, when you have these messages, that means it's not quite good. It also gives you the direction to fix the problem. It said, okay, problem involving the following parameters. Parameter 16, gender. So where's the parameter 16, gender? So in the last part, it gives you the technical output, parameter specification. You only need to find out 16. Okay, so we have so many parameters, all of these parameters. Okay, this is a intercept part, lambda part, all of these are lambda part. And then we have theta part. We have alpha, also the mean part. Data matrix, okay, sign matrix. So here, the sign matrix, parameter 16, gender, the variance, residual variance of sign, residual variance of gender, and sign matrix 16. But actually, when you look at the residual variance of gender, residual variance of gender, it's okay. Starting values, maybe the starting value is not so good.
Newton and Newton on their website for this error say that it's in the eigenvalue.
Yeah, the eigenvalue, the condition number here, this is too small.
Yeah.
It gives us the matrix is non-positive definite. First order derivative product matrix. So that's why I just said it may be a problem. But when you look at the result, actually it's positive. Okay, so
that's what it is. It's the you treated gender being treated as a binary, as a continuous variable instead of a binary variable.
Yeah, gender here.
So we need to tell it it's binary.
Gender.
So you have to restructure or recode gender into binary, right? Instead of
I'm assuming you would code it. I'm assuming there's only two.
Yeah, so it's gender independent.
To model it is kind of
Yeah.
which you do by.
Yes.
Did you use it as a in the with statement?
Yes. With.
Yeah. So it says that when it treats binary covariates as continuous if you put them in a with statement with other covariates.
I see. So here we use with to treat the gender as continuous, but actually it's a binary outcome.
Yeah, so it said it should be removed. That should be removed because it's an independent variable and it's automatically correlated with the other. It's automatically correlated with other covariates.
Let's try to remove. Okay, thank you. So let's try to remove with and plus. I just okay. So go back to the M plus and open the file. So suppose this one has been removed. So you can add this comment to remove the statement. Let's try to log it in. Yeah, we don't have the warning message here. Not good because we didn't. So here the model estimation terminated normally and the results. The result didn't provide the variance of the gender here in this case. So let me make it larger. Okay, so if you have the code without this statement, everything's okay, but we don't have the variance of gender.
You still get it up in the univariate variances.
Yeah, so we have the univariate, residual of the unifactor residuals. Okay, so for these three, we don't have the variance for age and not age, gender and EDU. Okay. But in R, we don't have this problem. Okay, so in R, we don't have any warning message here. When we check the variance, the gender, the variance of gender is still here. Yeah.
That's the variance. That's the same. That's the univariate variance.
That's the residual part. But gender is observed. We don't have the residual of the gender, right? We have the residual size for the observed test. These three tests are reported here. They are all positive. But in M plus, we said it's a residual of the gender. Why do we, oh, maybe we have already treated it as a continuous, so that's why we have the residual estimate.
Yeah, so it treated it as continuous. When you put it with a with statement, it treats it as continuous.
So that's why we want to estimate as a residual.
That's what I was trying to do that before.
Ah, okay. Yeah, thank you. That's very good note. Yeah, notice. Yeah. Thank you. Okay, so we have already finished the session 1. Yeah, here we have slides, but actually we have already done the comparison. So we have 3 software, okay, M+, Logon, SEM. Frameworks, we can do the comparison. Model fit, we can do a comparison to see if we have the exactly the same result or not. Okay. We have already done this part. Okay, so last slide is for the interpretation. So how are we going to do the explain the result? So for example, the model fit. IMSE is 0.056 and SRMR is 0.021. So you can say that this is not a good model, but it just fits the data fairly well. It's around 0.05. It's less than 0.08. Okay, it's not less than 0.05. Okay. It's around 0.05. So you can see that the kind of model fits fairly well, not very good. Okay. And the coefficient, okay. So the coefficient from gender to reasoning ability is not significant. So let's just look at the from gender to reasoning. So here, gender. Okay, this is the coefficient from gender to. Okay, this is the regression. R is based on these 2. Okay, these are 2 causes. Gender gonna cause reasonability. EDU gonna cause reasonability. But when you look at the EDU, it is significant. It's positive, it's significant. What does that mean? With a higher level of your educational level, the reasonability is significantly higher. So this value is higher with the EDU value. This value is higher. The R is significantly higher. Okay, 1 unit higher. If you increase 1 unit value of EDU, the reasonability will be 0.776 increased. Okay, and the change is significant. So that means the educational level gonna increase the reasonability significantly. But not gender. Look at gender. Gender, the coefficient significant of the coefficient is not significant. So female and male will not have significant difference, okay, on the reasonability. So it doesn't matter if your gender is male and female. The reasonability will not change significantly. So that's the result. The coefficient from gender to regression ability is not significant. It indicates there's no gender differences in R, the reasonability. R means reasonability. But education is positively related to R. Okay, education. So for the people with higher educational level tend to have higher reasonability today. So you are a PhD student, so the reasonability is much higher than master student and also higher than the undergraduate student.
Way higher than my ex-wife.
Congratulations. Okay, so that's the session 1. So any question? And of course, when you do the report, this is just only part of the result interpretation. You should explain all these numbers, okay? The factor loadings, the coefficient, regression coefficient. So what does that mean? So we should do the explanation. These are important outcomes because these are our findings. Okay? So any question? Okay, then we can have a 15 minutes break and we're gonna go back to the MTM table, okay, MTM table. When we talk about the validity, we have a table called MTMM, okay, multi-trait, multi-methods. Okay. So the data basically are collected by different methods and they're trying to measure different traits, okay, multi-traits, multi-methods. And we're trying to use that to explain the convergent validity and the discriminant validity. Okay, look at the correlation as big enough or small enough. So we have this example. So we have different blocks. We have here in this case we have 3 methods. Each method we try to measure 3 traits: trait A, trait B, trait C. Okay, 3 methods. 3 traits. So in total, we have 9 by 9 correlation matrix. And we have some hetero method blocks. We have hetero tree, hetero method triangles. We have validity diagonals. We have different names. In that class, we didn't talk about any factor analysis. But I said, okay, we're gonna go back to this example again. We're gonna use factor models to do further analysis. Yeah, so when we talk about this validity, I said, okay, so this is a method with some advantages and also with some disadvantages. For example, advantages include it can just convergent and discriminant validity simultaneously. So by looking at the numbers, for example, this number should be large. Okay, these are the liabilities. This number should be large, and this number should be small. Simultaneously, okay, check both validities. And also it can adjust the importance of method of measurement, provide a rigorous standard for construct validity. But we do have some disadvantages. For example, it's harder to implement. Okay, it's not known. It's not known overall statistical tests for validity. We don't have tests. We just look at these numbers. We said big, okay, but how big? How big is enough? It said small, but is that small? What number is small? Okay. And the requires a judgment call on interpretation. So that's not good. And then today we're gonna use another method called the correlated tree and the correlated method model. Actually, it's just the application of the factor model to do the data analysis. Yeah, CFA. Basically, we use CFA. Let's look at the Boland's example. This example is from Boland's textbook. Okay, so Boland's textbook, we have 4 traits. We're trying to measure 4 traits. We use 3 methods. Which 4 traits? Prominence. Okay, trait 1, prominence of a participant. Achievement of a participant. Okay, trait 2. Affiliation, trait 3. Leadership, trait 4. So we're trying to look at these 4 latent traits by using self-rating, peer rating, observer ratings. Okay, so self-rating, you should give these scores of these 4 traits, and peer rating also provides these 4 scores. Observer, the third people. Okay, so give the score of these 4 traits. So that's what this is a background of this example, and sample size, okay, 240, okay, 240 group members. So this is a final result. So we have the correlation table. So we have 4 traits measured by, okay, scored by itself with the person itself. So A1, B1, C1, D1. So this is the correlation matrix. We have these 4 traits. So this is the final summary. So this is a correlation matrix. Okay, this is correlation. This is the treatment by itself, and here this is the 4 traits. This is for the peer rating. Okay. From 5 to 8, these are for peer rating scores. These are from observer ratings. Okay, from 9 to 12. So 3 groups. Each group will have 4 traits. And do the correlation. For example, this is a correlation between self-rating prominence and peer rating prominence. Okay, this is a correlation. And let's take this one. This number is the correlation between achievement axis. Axis is peer rating. Okay, peer rating, achievement, and X4 is leadership self-rating. Okay, so all the numbers are listed here.
Is that how you do a correlation matrix for like a publication? That's how you would kind of spell it out?
Yeah.
Wow.
Okay. Now that's a
Sorry.
yeah. That's a problem. We only have this correlation table. We don't have the actual data. We don't. Although we have 240 participants to provide the data, but we don't have the actual data. So how are we going to do the code? So in the M plus, we are how going to code by looking at by only using the various matrix. Okay. So let's try to look at the test diagram. So in order to do the data analysis, we actually were trying to run set the model like this. Let me try to draw the test diagram here. Let's use so here we have different sets. We have A1. Let's try to use A1, B1, C1, D1. Okay, because in the original table, in the textbook, it just from X1 to X12. So it's 12 by 12 matrix. Let's try to make it easy to group this as method 1, group this 4 as method 2, group this 4 as by using method 3. So A, B, C, D, 1, 3. So we have A1, B1, C1, D1. These are from first method. Okay, so these are from this is from method 1. This is the first latent variable. Okay, so method 1 gonna inference these 4 observations. And we have A2, B2, C2, D2. This is method 2 gonna inference these 4 outcomes. And we have B3, B3, C3, D3. So method 3. So here, this is here, this set. This is a observer rating will influence the 4 observations here, 4 outcomes here. But we do have another trait, A trait. What is A trait? It's A trait. What is A? A prominence. Okay, prominence A. Prominence gonna influence the A1, A2, A3. Of course, the people's prominence will influence their score. A1, A2, A3. And B, the achievement will influence the outcome. B1, B2, B3. And C, affiliation will influence the people's C1, C2, leadership, okay, leadership D will influence D1, D2, D3. Okay, so we have the awareness among them. We have some awareness among them. What is our model? Okay. This actually is a bifactor model. Bifactor, okay, not second order factor model. This is a bifactor model. We have the same observed variables here. We have method factors. We also have attributes, traits, factors. It's the same model. So this is our test diagram. Now let's have a review. So when we talk about bifactor, when we talk about the difference between second order and the bifactor model, we have these two test diagrams. So suppose we have items, these are observed variables. We have first order factors, and then we have second order. This is called the second order, higher order, okay? Higher order. But here, we have the same items here. We have factors checked here. We also have the other factor checked here. So this is called a five-factor model. So currently, we are using the five-factor model. And that's the data form. Okay, so I just copied this number from this table. This table is from this page is from the textbook. So I just summarize these numbers by using the numbers matrix here. That's it. The data form. Now the problem is how are you going to treat this as our data to do the data analysis without the original raw data? This is a trick. Okay, this is a trick. In M+, we're gonna use a type. Okay, same thing. Okay, we have title, we have data, the data file here. But in addition to the data file, we're gonna specify. We're gonna tell M+, the type of the data is correlation matrix, not the raw data. Okay, we have a keyword type. We have keyword type. Type correlation. Of course, it can be some other outcomes or options. I will show you the different options. In this case, it's correlation. Correlation. Okay, off diagonal elements. Sample size. In addition to the correlation, we also need to tell M+. What is the sample size? Number of observations. Okay, and number of observations is 240. This is the sample size. And then, what are our variables inside of the correlation? A1 to B1, the first set, okay? A2, B2, the second set. A3, B3, the third set. We are going to use all of these variables, okay? All of these variables in our model. So use variables and put everything. And okay, we can just run the analysis. So here, the keywords. Keywords. Here we use a correlation. Of course, we use CORR. It's a short for correlation. You can also use a correlation for whole name. It's for off diagonal. So the half of the correlation matrix. Look at the data here. Okay, you only have the half of the matrix information. You didn't include the half, the upper half. If you also include the up triangle, if you have the full matrix, then you're gonna use a full correlation. You're gonna use this option, full correlation. That is a full matrix, not just the half triangle, the lower triangle. And if you have the covariance matrix, then you're gonna use covariance. Of course, if you only have the lower triangle, then with these keywords. If you have the full matrix of covariance table use 4 covariance. Okay, we have different keywords here based on different types of your data. In this case, just pure operation. Okay, half triangle, lower triangle. That's it. And number of observations. Okay, number of observations. Okay, 240. Okay, that is information we need to tell and plus. Finally, we have model. Okay, so that's not end about the code. Okay, what's your model? Okay, what's your model? This is a model. Okay, it looks pretty, but let's try to understand what does it mean. Okay, model. M1 by A1, B1, C1, D1. What does that mean? That means M1 is a latent variable. It's newly created. M1, this is a new variable. Latent, okay? It's latent. And it's defined here by using by statement. M by, okay, A1, B1, C1, D1, so it just tells us this part, okay? It just tells us this part. M2 by, okay, M2 by these two, okay? M2 is created here by using by statement. It's latent. M3 by, okay, M3 by this 4. That's the right side, the method part. And also, we have the T. Okay, so here we use A, B, C, D, but here we use T, doesn't matter. Okay. Trait 1, it's also the new defined latent variable. It is measured by A1, A2, A3. In the code, we use T1. Okay, yeah. So we can just treat it to T1. Treat 1 is A actually. Treat 1, treat 2, treat 3, treat 4. Treat 1, treat 2, 4. Measured by A1, A2, A3. Okay, T by these 4, these 3. T3 by these 3. Okay, T4 by these 3. And you can see that all the factor loadings are freely estimated. Okay? So we have from star. Okay, so all of these factor loadings are free. In addition to this, we also have, okay, here, M1 to M3 with T1 to T4 at 0. What does that mean? We assume that these two parts, method and traits, are independent. M1 to M3, these 3 factors, and T1, T2, T3, T4, 4 traits are independent. The covariance fixed at 0. No correlation between them. Okay, I cannot say that the T3 is correlated with M2. No, I don't have this assumption. Independent. Variance of M1 fixed at 1. Variance of M2 fixed at 1. Variance of M3 fixed at 1. So all of this variance fixed at 1. Variance fixed at 1. Variance fixed at 1. Here, the same thing. Okay, so variance of treatment 1. Variance of this written treat are fixed at 1. Variance of this method fixed at 1. Okay, that's the meaning of these 2 parts. And then these are covariance. Okay, these are residuals. These are residuals. A1 to A3. Okay. Residuals, all of these are residuals. A1, A2, A3. Okay. The various are residuals. B1, B3, okay. C1, C3, D1, D3, the residual variance. These are covariance between traits, okay. Trait 1, trait 2, okay. Trait 1, trait 2, covariance. Trait 1, trait 3, covariance. Trait 1, trait 4, 2, 3, 2, 4, 3, 4. The covariance matrix among traits. So that's the part of here. And also we have the part of methods. Okay. Method 1 with method 2. Method 1 with method 3. 2 and 3. So that's it. Covariance, residual variance, variance, independent, these two parts, and bifactor, two parts of factors. Okay, trig factors and the method factors. So that's it. That's our code for bifactor model. So I have the table here, so please download the code and the file from the LC. It's called, I think it's called CTCM. Okay, the data file is called M plus MTMN. CTCM.INF, input file. So that's it. This is the input file. Yeah, so that's we explain. Here the keywords, okay, type is correlation. If we check the data file, M plus MTMN, okay, so MTMN. That's it. This is our data file. Only lower triangle part of the whole correlation matrix. So that's why we have a correlation. Number of observation, 240. All of these names are names, okay? Names. And these are our model statements. Yeah, we can try to click the run. That's it. This is our outcome. Okay, so the beginning part is a review. This is the input file. So number of groups, 1. Number of observations, 240. Number of dependent variables, 12. Okay. In this case, we have 12. All of these 12, okay, 3 by 4, okay. All of these 12 are dependent variables. Dependent variables. Or just indicators. These are indicator variables. And then we have number of independent variables, 0, okay? We don't have on statement, so independent variable, 0. But we created some latent variables. Okay, so number of continuous latent variables, 7. We have 3 methods. We have 4 traits. Add them together, we have 7. 7 latent variables. So all of these are continuous dependent variables from A1 to D3. Latent variables, okay, 3n value, 4 traits. Algorithm. Now we have this warning message again. Let's try to look at the result first. Model-fit information, okay, model-fit indexes. RMSCA right here. CAFI, TLI. SR norm. Model result. Okay, so these are vector loadings. M1 by method 1 measured by these 4 observed variables. Okay, A1, B1, C1, D1. The vector loadings. And then P value, P value. Method 2 measured by these 4. Method 3 measured by these 3. Trait 1 measured by these 3 traits. Okay, this is the prominence scored by P itself. Prominence scored by peer. Prominence scored by an observer. So this is the prominence of the written trait. This is the whole thing. That's the loading here. This is T2 is achievement by these three groups. Affiliation measured by these three groups. Leadership measured by these three groups. And these are columns, okay? Method 1 with T1, T2, T3, T4. It's 0 because we assume method and trait are independent. No correlation among them. So method with traits, either T1, T2, T3, T4, all of these 0, 0, 0, 0, okay? No relationship. But M1 with M2, this is a correlation. M1 with M3, this is a correlation. Same thing, M2 with T1, T2, T3, T4, no correlation. Method 2 without, okay, with no correlation with the traits. But M2, M3, correlation. And M3 with T, no, okay, all 0, 0, 0, 0. T1, okay, T1 with T2, T3, T4, okay, trait 1 with the remaining traits. Correlation here, correlations are here. And T2 with T3, T4. T3 with T4, okay. Actually, you can see that the T1, T4 are quite high. T1 is prominence, T4 is leadership. So these two are quite highly correlated. But T3, but T2 and T3, so trait 2 is achievement, and the T3 is affiliation is not highly correlated. Affiliation and achievement 3.361. And the variance are all fixed at 1. Okay, variances of these 7 vectors are fixed at 1, 1, 1. Residual variance, okay, residual variance for these 12 items. So these are psi matrix, this psi matrix, okay. Okay, this is the outcome, but the problem is how to understand these numbers. I have some tables for you. So in your final paper or in your journal articles or manuscript, the dissertation, you should report this table. Okay, so let's look at this. Okay, so this is a bar table. That means we have some factor loadings here. So method 1, we have different indicators. Method 2, we have different indicators. Method 3, we have indicators. Trait, we have trait 1, 2, 3, 4. The method 1, 2, 3. So how to fill out this table? Okay, that's it. I have some examples for you. So what does that mean? So trait, here, trait 1, T1 is measured by A1, A2, A3. So trait 1 is A. The prominence is measured by A1, A2, A3. So this is the factor loading from the M+ table. So if you go back to M+, traits, yeah. Here, that's it. T1. The trait 1 prominence measured by these 3 observed variables. So these are loadings. You can just put these loadings into that table. Okay. 0.409, 0.503, 0.503. It's here, okay, 0.409, 0.503, 0.543. So these are 3 factor loadings. And treat 2, achievement is measured by B1, B2, B3. Okay. So, if you go back to then plus, achievement 2, achievement, measured by B1, B2, C. These are 3 numbers. These are 3 numbers. And you can just fill these numbers here. Okay. 0.281, 0.128, 0.521. These are 3 factor loadings. And continue. You can compute the table by looking at the T3 is measured by C1, C2, C3. T4 is measured by B1, B2, B3. So you can fill out these numbers. So what are these? The same thing, okay? Methods. Method 1, self-rating is measured by B1, B1, C1, B1. So look at the result. M1, okay? M1, method 1, self-rating is measured by these 4 scores. Okay. B1, B1, C1, B1. So these are numbers. 0.655, 0.678, 0.602, 0.716, 717. It is here, okay? 0.656, 0.678, 0.602, 0.617. These are for method 2. Method 2 measured by this 4. Method 2 measured by this 4. So you can continue. Finish this. This is for M2. Let's finish the table 5. Table 5. And you can also figure out images. What is a image? The image is the covariance among factors. Covariance among factors. So we have 7 factors. 4 P, 3M, 4 P, 3M, total 7 factors. So what are these factor covariances? So that's it. So, but first, okay, method and T are independent. So all of these are 0, okay? Method and traits are independent, 0, 0, 0, 0. But within T, okay, within treatment, we do have some covariances. Within M, okay, within M method, we have some covariances. How to identify, how to obtain those numbers? It's also here. It's a okay, M1, latent factor M1 with M2, M3. This is for M2, this is with M3. Of course, all of these are 0, 0, 0. 0, 0, 0. So, 0.53 is a covariance between M1 and M2. 0.587 is a covariance between M1 and M3. Okay, that's it. Okay. 0.53 is a covariance between M2 and M1. 0.583 is a covariance between M1 and M3. And you can also figure out this one. This is the covariance between M2 and M3. It's here. It's here. M2 and M3 covariance. And same for trait. Trait. Here, this is a trait. Trait. Among traits, trait 1 with all of these 3 traits. So these are numbers inside this part. Okay, 0.755, 0.857, 859, 0.932. These are these 3 numbers. Covariance among traits. These are covariance between T2 and T3 and T2 and T4. T2, T3, T2, T4. But here, this just means that. We see the covariance between T3 and T4. Okay. T3 and T4. That's it. That's it. So this is a phi matrix. Phi is a covariance matrix among factors, 7 factors in this case, 7 factors. Of course, all of these are symmetric. Okay, you can fill out the up diagonal part. In addition to this table, we can also fill out the side matrix. What is side matrix? Residual variance. Residual variance is here. Residual variances. Okay, here. Residual variances. We have 12. Okay, we have 12 residual variances. So the diagonal elements are just these numbers. So if we just copy the numbers here, yeah, this is the first element inside, this is the second element inside among B1, B1, B1. And we also have C1, C1. Yeah, we just continue. So I'll continue. So this table is sign matrix, residual matrix. Just by doing that, we actually figure out all of these matrices. And that is the code, and this is the output tables. Yeah. And yes, I think I explained this. And by looking at the fact loadings, we can tell, we can have the significance. Is significant or not? Okay, we can do the test. Okay, so if we look at the output here, so we also have the standard error, yeah, the z values, the p values. So it is significant. Okay, for example, all of these are significant. All of this is significant. So in addition to the correlation numbers, we also have the spectral loadings, and we can clearly see that is that significant or not. So the model is described by this type diagram.
Okay.
Any question?